Okay, so we're going to start chapter 23. In 23, we're going to dive into electric circuits. And so far we've talked about current just as a thing. We've talked about charge, stationary charges, a moving charge. We call that a current. But if we're going to create some device and use those currents to do something useful, we need to put it together in a circuit. That's what this chapter is all about. This is one of my favorite circuits of all time. This is a 1965 Deluxe Reverb guitar amp made by Fender. This is a picture of the insides, and the point is, I showed you the insides of one of my guitar amps that I made, but the point is, it's a whole bunch of components, right? Variable resistors over here. These orange guys are capacitors. There's a little resistor there. Bunch of stuff we've learned about. Now, this is a pretty complicated circuit, and just looking at this picture here, boy, you'd have a hard time wrapping your brain around that. So, we want to introduce the idea of a schematic. This is an electrical drawing, and it's a drawing that shows all of the electrical relationships of that circuit. It doesn't show where the things are physically, right? So this is not about physically where the components are. This is all about electrically. What are the electrical relationships going on? And so this is a much more complicated circuit than we will analyze in this class. But my point is that the tools we will learn in this chapter will help you, are enough for you to learn how to analyze a more complicated circuit if you ever needed to. And looking at this circuit, we see some things that we are familiar with. Each one of these little parallel lines here, that represents a capacitor. And this is a capacitor that is 0.001 microfarads. Okay. Each one of these squiggly lines, that is a resistor, right? So here we see another resistor, a capacitor, another resistor. This right here with the arrow, that is a variable resistor. Now there's some components in here that we haven't talked about. These are the tubes. These are the famous vacuum tubes, which guitar amps use, and in the old days, all electronic circuits used it. Those function as like a valve. We're not really going to learn too much about that, but it's almost like a valve on your hose where you can turn it up or you can turn it down. There's let's see, this right here, this little symbol right here, that is a loop of wire that indicates an inductor. We will likely learn about that in our chapter on AC electricity. At any rate, this is a schematic of this circuit. We're going to learn a little bit about these schematics and these symbols and how to put together a circuit. So first of all, we need to, here's a simple circuit, okay? So we've got a resistor, a battery, and a capacitor. Now, this picture here, it shows us what we've got in our circuit, and it's a nice picture, I suppose, but there's a lot of details here that we just don't need. We don't care whether this is the plates of this capacitor are square, or if it's more of one of those round style like I had shown in class. We don't care if it's a AA battery or a 9-volt battery. We don't care, I guess we care, we don't care about the shape of the battery, I guess. We don't care about the shape or the size of the resistor. We don't care if the resistor's over here or over here. At any rate, there's a lot of stuff in here that we just don't need to have. The literal picture provides many irrelevant details. So what we would want to do is we really want to create a drawing that includes only the information we need and none of the information we don't need to make it a little bit easier to see. And so in order to do that, we are going to introduce these schematic symbols. So these schematic symbols are the basic drawings used for drawing electrical circuits. A battery is drawn like this. A couple of things to note: that it is a series of long and short lines. We'll see that a capacitor is two parallel lines that are the same length. These are lines that are different lengths. And the positive side of the battery is indicated by the longer side of the schematic. So this is the high potential side, or the positive side of the battery. This is the low potential or negative side of the battery. A wire, we just represent with a line. That one's easy. A resistor has these little squiggles. Okay, in our book, they are shaded, and this is consistent. The book will always shade the batteries with green. It will always shade the resistors with red. That is specific to our book and is not standard notation. Otherwise, the black lines here, the squiggle for the resistor, that is standard notation. A light bulb is a little squiggle like this. Here's a junction. That's just two wires intersecting. A capacitor is two parallel lines. And again, the shading with the blue, that is specific to our book. Notice that the battery has the longer line and the shorter line, and the capacitor has two parallel lines. Again, here's the schematic for my guitar amp, and there's a capacitor there. There's a resistor there. Exactly the same, but without the shading. A switch looks like this. A switch is essentially a wire that can be broken. So, back to this picture. Here was our physical, literal picture of the situation, and here is our schematic representation of the situation. What does it take to make a light bulb light? Does this light bulb light up? Why don't you pause the video and consider it? Well, indeed, it will not light up. And to think about why not, because it's not a complete circuit, right? Charges can enter here, I suppose, but they cannot leave, right? We need to have a complete loop in order to complete that circuit. So, in order to complete the circuit, we have our light bulb on here like this. We would have to run a wire from the negative side of the battery to the side of the light bulb. The current could then go through the filament and back into the light bulb, or back into the battery. Okay, so it's not a complete circuit. In other words, just a basic thing. We've got to have a circle where the charges can flow in order to have a complete circuit. And again, if you believed me about the conservation of current and the conservation of charge, then I feel like you have to believe me about this. Because otherwise we'd have a buildup of charge in our light bulb. It just doesn't make any sense. You got to have a complete loop. Okay, this is a review slide, Kirchoff's junction rule. We already learned about this in the last chapter. It says that the currents into some junction always equal the currents out of that junction. And again, this is just a statement of the conservation of charge. Let's practice using it real quick. Here, the diagram below shows a segment of a circuit. What is the current in the 200 ohm resistor? Why don't you go ahead and pause the video, and I'll see you on the other side. Okay, here's our picture. Where is our junction that we're talking about? Well, let's look at this junction right here. We see that coming into the junction, we have 2.5 amps. Out of the junction, we only have 1.5. Well, that obviously doesn't work. We need to have a little bit more coming out. How much more? If this carries 1 amp, then we have 2.5 amps out and 2.5 amps in. Woohoo! That works. Not too bad. So that's Kirchoff's that's Kirchoff's junction rule. Kirchoff has another rule called the loop rule, which it's just a little bit trickier, but it's still not too bad. Okay, let's call on our analogy where we're treating potential like the height in an electrical landscape. So notice that Kirchoff's loop rule is all about a change in potential. So I'm not going to talk about a change in potential for a minute. I'm going to talk about a change in height, right? And so if this is my beginning location, right here, I'm at my beginning location, and I go in some closed loop. I don't know, I'm going to go over here. Oh, I'm going over here. I'm behind my chalkboard. Now I'm coming around. Okay, I just crawled up on a chair. Oh my gosh, now I crawled down. Okay, now I'm... Okay, I'm back where I started. Here's the question. You ready? What was my total change in height? I know it's tricky. If you answered 0, you're right, because I'm back where I started, right? I'm back where I started. See, it doesn't matter where I go. If I end up back where I started, what's my change in height? 0. Every time, right? Here's another path. I start here, I go up, oh, here I'm on my other chair. Okay, now I'm going on to this chair, okay? Okay, oh, now I'm going back. Oh, this one's going to be really tricky. I'm going to go back. Oh, there we go. Okay. Back to where I started. What was my total change in height? If you guess 0, you're right. It just makes sense, right? If I go in a closed loop, my change in height has to be 0. Unless I started from an elevator. That doesn't even make any sense. If I made it back to exactly where I started, my total change in height was 0. It seems so obvious if I'm talking about height in a physical object, me, moving from one location to another. It's hardly even worth talking about, right? But the same thing applies to an electrical circuit. So let's go back over to the PowerPoint here and see that if I start here and I go around in a loop, well, guess what? I ended up where I started. So what was my change in height or potential? 0, it had to be. And it's a little bit harder to see because, these electrical ideas are so abstract and we have so much less experience with them. But the fact is, the potential at this point right here is defined by a value. I don't know, maybe it's 1 volt, right? So that means that if I go around this loop and I come back here, then I'm back to that same potential. If it was 1 volt before, it is still 1 volt. And what do I mean by go around? It says for any circuit, if we add up all the potential differences, that's what we mean. So when you say start and end here, we're talking about going around the loop, adding up all the changes in potential. Right. So similarly, for a second ago, if we were to go, the example that I did walking here, right? So I had 0 change in height as I walked around the back of my chalkboard. When I came around here, I had a change in height of plus, 1.5 feet when I went up the chair. But then I had a change of negative 1.5 feet when I went down the chair, leaving me with a total height change of 0, right? So if one of these delta V's is positive, then at least one of the others has to be negative, right? So if you go up a little bit, you got to go down a little bit. But it's the same idea. Again, we see this summation notation. Makes it look trickier than it is, I think. If we add up the potential difference of all of the components around the loop, then we will get 0. That's what it says. So this is another one of those that seems almost like, why do we even have to talk about that sometimes when we introduce it? But then when you go to do it, it can be a little bit tricky. Again, here's a more realistic circuit. Here we have a battery and a couple of resistors. So as I imagined traveling around the circuit, it's a journey of the mind. There's no real thing traveling. If we take a journey of our mind around this circuit, if point A is at 0 volts, then we see that we have increasing potential as I go through the battery. Again, across the ideal wire, no change in potential, because ideal wires have 0 resistance, therefore 0 potential difference, even when there's a current flowing through them. So no change in potential across the wire. When I get to C, I enter the resistor and I see the potential drop as I move across the resistor. As I move across R2, I see the potential drop some more. And then I get back to E, where the potential is the same all the way back to A. Again, I ended up at the same potential that I started at. This is the nature of the loop rule. Notice that if I had started at D instead, I just would have gone down first, back to A, up, and then down a little bit more. I still would have ended up where I started. There's nothing magic about starting right here. It doesn't matter where you start. If you get back to the same spot, your total change in potential would be 0. So we could break this down into a list of steps. Draw your circuit diagram. Assign a direction to the loop of the current. In other words, we're going to try and pick what direction the currents are in. Now, this can be a tricky step for some students because sometimes you don't know, especially in a more complicated circuit. You just don't know what direction the current is going before you do the math. You may need to do the math to figure out what direction the current is going. So that's okay. If you don't know the direction of the current, just guess. And then if you're solving for the current, you'll get to a point and you'll say, oh, I got the current, it was negative 10 amps. Oh, that negative sign indicates that you just picked the wrong direction. That's all. The 10 amps is still correct, you just picked the wrong direction. We'll talk a little bit about that in a minute. You travel around the loop, step 3, that is a journey of the mind. Delta V across a resistor is positive if you're going against the current and negative if you're going with the current. And we're going to be wanting to use Ohm's law for that. So for step 4, Ohm's law, delta V equals I times R is real important for that step 4, right? A lot of times you'll know the resistance and the current, and you'll be able to calculate the delta V, or maybe you'll know one of these and you'll have to use the other as the unknown that we're solving for. At any rate, our delta V across a resistor is given by this equation. So this equation shows up in the loop rule all the time. Delta V across the battery is positive if you're going from positive to negative to positive, and it's negative if you're going from positive to negative, okay? And then we apply the loop rule. The total change in potential around any loop, closed loop, is 0. Okay. Let's try a quick example. There is a 1 amp current flowing in the circuit. What is the resistance of the unknown circuit element? Well, first we should just draw a picture. And even if you have one on your piece of paper, it's good to draw it. Even if you have one in the book, it's good to draw it on your piece of paper. Okay, here's our schematic. The first thing we should do after we've drawn our picture is we should assign a direction for the current. Okay, so let's assign a direction to the current. Real quick, in your mind, is this current going to flow clockwise or counterclockwise? I think it should flow clockwise, and here's why. Because it always flows through the wires from high to low, which means it's going to go like this. Through the wires from high to low. So the direction of our current will be like this. Now, if we guess wrong, that's okay. We just end up with a negative value in our answer. Okay, so here is our current, and it is 1 amp. Now, let's apply the loop rule. I'm going to start right here, and I'm going to go around the loop like that. Okay, the first element I get to is the battery. I'm going from low to high, from negative to positive. Therefore, it is a positive voltage. I should write 9 volts. Okay, next element, resistor. I'm going with the current. Now imagine that you went up the Poudre River one day. The river is flowing in this direction, and you are walking in this direction. Are you walking uphill or downhill? If you are walking with the current in the river, you are walking downhill because water flows downhill. Similarly, current flows from high potential to low potential, so if I'm moving in the direction of the current, I am going downhill or down in potential. I should write minus. Now, we're going to call on Ohm's law. Delta V equals I times R. In this case, we know what I is and we know what R is. We can plug them in. 1 amp times 3 ohms. Great, that is that element. The next element we get to is this resistor. Again, I'm going with the current. If I'm going with the current, the potential is decreasing. I should write minus 1 amp times 2.5 ohms. And the last element we get to is this. Again, I am going with the current, so I'm going down in potential. You might say, I don't know what that resistance is. How can I calculate the potential? You don't know what it is. We're going to plug in I times R so we have something to solve for. Minus, because we're going downhill, 1 amp times R. And I've made it all the way around. I should set that all equal to 0. So 0 equals my total change in potential. And now I can just do some algebra. All right, so we ran our calculator, did a little algebra. We got 3.5 ohms for our resistance.